do it this way, but I figure this is better because we had a lot of folks that were absent on Friday for various events and all that kind of good stuff. But this way we could keep moving forward, and they could get their test done at the same time, and they could just watch this when they have a free moment. So this next chapter that we're going to learn about is about light and light waves. This kind of gets into a little bit of the physics stuff again, um, some real basic equations, and what we're going to get into is how to manipulate those equations and their relationships to each other, to the different parts, kind of like what we did uh, last chapter. So yeah, here we go. So light in the electromagnetic spectrum, light radiation, electromagnetic waves. It's all kind of your basic concept here. Light comes from many forms. Again, we're not going to get too far into the physics area of this. We're going to kind of focus in on how it relates to chemistry, but this is again one of those things that if you're going to move on, um, either to AP Chem or physics, especially, you'll get a little bit more of this later on as you move forward. Um, Light, as we're going to find out, actually works in a couple different ways. First, it kind of travels a wave. We think of waves like this. Again, when you move to physics, you'll learn what's going on here with waves traveling through other mediums. And it Light can carry a lot of energy. That's why we can have solar panels and convert that energy into other electricity that we can use for other things, like powering your iPods and all that kind of good stuff. Uh, Again, you can pause this and go back at any time. Uh, so don't worry about that. We have a couple terms that we're going to have to memorize. These are going to be really important because we're eventually going to use these in our mathematical equations. And when you're solving problems, you're going to need to be able to easily go and understand what is what. Wavelength is when you go between two peaks. So you have one peak here, one peak here. We usually describe these in nanometers because even centimeters is too big to really get a good scale on this. Amplitude is your space between the halfway part of your crests or peak and or the troughs. We're not going to talk a lot about them. You'll get into this a lot when you make it into physics. Uh, Period, same thing. We're not going to talk too much about, but just so you have a little bit of understanding. But frequency, we are going to talk about. This is the number of waves passing in a given amount of time. So if you have a fixed point, uh, if you have a fixed point, let's say right here, and this wave was moving from left to right, then you would count how many crests hit this wave at the exact same time. In fact, we have a nice little. This would. Oh, I need to stop drawing. You'll find that I'll do this a couple times as I get used to this again. So our frequency here, we have our fixed line. This wave is moving. We would count the amount of crests that are hitting in a given amount of time. So you would count like 30 seconds a minute. So this one has obviously a lower frequency, so lower notes if you're a band person, than this one, which has a higher frequency because you're obviously having more crests hit this line per second than up here. So that if again you're into musical notes, this is going to be your higher pitches and that kind of thing. Uh, so some of these wavelengths of light. This is your Roy G. Bev. Remember, there's no I in there, so red, orange, yellow, green. Um, we usually don't count the I here in chemistry because indigo and violet are too close together, so we're not really going to count that. This is kind of your standard that you've probably seen in a lot of other classes, but again, we're going to drop the indigo. So in your notes, just put, you know, BV here. Um, And this is, again, as a kid, you're kind of taught to draw like these colors as individual ones to make a rainbow, but as you can see here, it's more of a continuous coloration, a gradient going from red to green. So again, these visible wavelengths have, if you were counting these in meters, see this is really small. That's why usually we use nanometers, and then the frequency we use hertz um, as our unit here, and then we usually convert this to nanometers, which is written as nm there, and again it's just a standard conversion metric. So again, there we go. And sometimes you could see that the hertz can be kilohertz, megahertz, or gigahertz, and your base level for that is going to be hertz. So again, your metric conversion is going to be pretty useful here. What you're going to need to know in the future here is that you have a lot of different wavelengths going from really, really short to really relatively long. Again, these are small, and then you have some that are really big, like some of your AM frequencies. So that's why AM radio stations go further. The ones you're going to need to know is infrared is right at the beginning of your visible frequency. So it's here, and then visible frequency is the next one. So remember, red is your longest wavelength in the visible, the ROI part, and as you can see, red is right here. So infrared goes directly to the left of red. So it's infrared, then red for your wavelength. Then you have BEV, which is violet, and then the one right next to it is going to be ultraviolet. And you might have heard of infrared like cameras that we have in use now, and then like ultraviolet light that we really can't see, but other animals we're starting to learn can. So if you go onto AP Bio, you'll learn a lot more about that. But what's going to be important for tests and homeworks is for you to understand infrared, as far as we're going to get into, is going to be the longest wavelength that we need. Then go through your visible spectrum, your Roy G Bev thing, and then ultraviolet's next, and that's kind of where we're going to stop for right now. There you go. Let me get all this off the screen. There you go. So what is light? I mean, we're talking about light. You obviously experience light every day, but what is it? This is something that I personally think is really cool. It's one of those things of nature that kind of gets me into science. Light is at once has the characteristics of a wave, so it has all those parts that we talked about, but it also has the characteristics of a particle, specifically photons with the electrons. So we're going to talk about the gentleman who kind of came up with a little bit more of this tomorrow. But for today, we need to understand that this actually behaves as two separate, so as wavelength or as photons as far as the energy is concerned. So this is what we're going to pick up in more detail tomorrow, but you should understand that you can treat this as two separate things, which again, for me, is really cool just to think of something as fundamental as light, just depending on how you interact with it, is going to behave in two totally separate ways. There you go. Hold on just a second. So we have a couple of equations for light. So again, this is why I said that it's going to be important for you to remember the terminology from a couple slides ago. When light is acting like a wave, and again, we're going to get into this a little bit more tomorrow, but let's just learn how to work with these equations today, and we'll go into a little bit more detail tomorrow. you're going to use this equation here, whereas lambda, this cool little Greek symbol here, it stands for your wavelength. So again, you're going to kind of want to use nanometers for that as your standard unit. The F, sometimes you could see it as a fancier F like this. You know, PowerPoint really doesn't let you do that too much, so it's kind of italicized F is what you have here. And the famous C, some of you may notice it from E equals mc squared. You know, Einstein's really famous equation there. And so a lot of people don't actually understand what this means or what the parts are, but as you can see, C is doubled up right here, and that stands for the speed of light. And this should be a subscript, so, or superscript, 10 to the 8th there. That's an approximation. It's actually like 2.99, and get a bunch of, depending on how many significant figures that you want to get to. But we're just going to use 3.00 times 10 to the 8th for our speed of light. What we want to understand here, so we don't get confused when we move to physics or if we are looking at other tutorials online, this speed of light is through a vacuum only, meaning through space or something where there's no other air, no other particles, no water, no anything else. Super important. Please make sure we underline, circle, italicize. I think I got some colors in here. Maybe this will help us out. You know, a little fireworky guys there. Look at that. There you go. This speed is in a vacuum only. So this is kind of your standardized version of it and kind of idealized. And again, when you make it to physics, you're going to learn about Snell's law and all kinds of cool stuff where, you know, light refracts, and if you're an archer fish, that's kind of your bread and butter. We're not archer fish, so we don't have to worry about that too much. Oh, well, we do, but okay. So if light is acting like a particle, so it's something that has a physical form, E, energy, is equal to H, which is Planck's constant, which is here, and I'm not sure why this isn't showing this as superscripts, but it's 6.63 times 10 to the negative 23rd joules per second. Look at that. So you have two equations now. Again, the important thing is that you know the equation and that you could plug stuff in. So you're using nanometers for wavelength, frequency is in hertz, and then you could bounce it back and forth between gigahertz and megahertz if you need to. And speed of light is, kind of standardized meters per second. And then Planck's constants here. I mean, again, we've talked about this, that if this is all we can do is just be able to plug and chug numbers into basic equations, we're sitting middle of the pack, and I don't know of anyone at this school who's happy being middle of the pack. So let's set ourselves apart just a little bit. We're done drawing. There we go. So, remember our last chapter, and we talked about inverse relationships versus direct relationships. And if things were multiplied, like Boyle's law, then you have an inverse relationship. Guess what? Don't forget those things. This is why learning versus grades are so important, because once you learn that multiplied things together generally have an inverse relationship, look at this. You don't have to relearn anything. You just have to reapply it to something new. So as your wavelength goes up, your frequency typically goes down. Again, think of, if you're in band or, bass guitar versus a really high pitch note where you could kind of feel that going through your body a little bit more. We'll have a couple demos coming up here on that. But again, and this is going to be proportionally. So if wavelength goes up by 2, frequency is going to go down by a half. again, if you remember your gas laws, you're going to be pretty good with all that. However, a particle is a little bit different. So again, remember what we did for gas laws, and we don't have to redo anything. H is what? I could hear you right now saying it, but please don't say it too loud because, there's people taking a test right now. If you're watching this after people are done taking tests, then, whatever. This is a constant, so we can just cross it off. Cool. And then where do we want to put things? On the left side of the equation. So now we can rewrite this. Energy over frequency. And again, remember your gas laws. When we had a fraction like this, we had what? We have our relationship. And what was that relationship? Again, I can't hear you because this is a video. So if you said that out loud, I couldn't understand that. But this is a direct relationship because we can rewrite this as energy over frequency. So that energy goes up, so does frequency, and we're keeping Planck's constant because, it's in the term. So again, you can rewrite this to have energy 1 over frequency 1 equals energy 2 over frequency 2. Same exact thing that we did for gas laws. So again, if we were worried about knowledge acquisition before, instead of looking at just getting a grade and spitting out numbers, look at us. You have a lot less to learn for this chapter. Now, even though light cannot act as a particle and a wave at the same time, there are a couple of things that can bridge this gap. Now again, we talked about this is kind of your first science course where you're having to kind of put an equation inside an equation. You've done it in some math classes, but not as much in science. Let's look at this. I'm kind of going all Bob Ross on this recording, so I'm sorry, but I've already 20 minutes in almost. I'm not redoing it. So there you go. Usually I'm loud in class, but I'm at my house and my kid is asleep, so not going to be super loud on this. But if we look, we have one thing right here. Boom. That is common. And unless you're into the wrapper common, which I didn't realize was a wrapper until my wife told me, and then I got made fun of for, basically living in suburbia versus the urban area and listening to rap all the time. I don't know. He's also an actor, I guess. We can rewrite things. Let's get that out of the way. So we can actually get our frequency, and then we have our speed of light over our wavelength. What can we do? Well, transitive property, that's right, math terms, means that we can now do this. Our energy is equal to Planck's constant times the speed of light over your wavelength. And that will give you the energy that is being given off by the particle, the proton. And again, we're going to talk in more detail tomorrow about what this actually means scientifically, but you need to be able to manipulate these equations and put them together and solve a couple of problems. And that's what we're going to do for the rest of the time when you're done with this. So again, we're going to move on tomorrow and look at Max Planck. And if you lived through the planking phase of, 5 years ago, that does not mean that you are the best at planking, but he is an actual gentleman that was able to see some of these relationships in more detail. So again, what you want to work with now is looking at these equations and seeing if you could solve for the different parts and be able to manipulate them, and that'll be your homework for tonight. If you have questions, please ask me, or you can always rewind and go over as much of this as you need.